Hello and welcome to lesson number 8. So for this one, I'm going to be trying something a bit different. I'm going to actually do a live coding demo, which you've told us has been helpful. And in this demo, we're going to review and put together a lot of the skills that we've covered in the past 2 weeks, specifically loading files with NumPy, working with NumPy two-dimensional arrays, creating date-time objects, and making some line and scatter plots. And I think this demo should be really useful for your assignment number 2. Before we go through this, I just want to suggest that you open up the accompanying Colab notebook, which has all the code I'm about to write. So you can take notes in that about what I'm saying as you follow along. And you can get to the notebook in the Modules tab of Canvas over here under Class 8. So we're going to open that notebook, which for me is blank still. And when you open it, in the File menu, if you go to Save a Copy in Drive, that will let you make your own copy. And feel free to pause this video to get everything set up. You can also add notes using Python comments. So, writing this as a comment. Another way, of course, is to use Colab's comments over here. And that's this little icon at the top right. Okay, so in this demo, I'm going to use the El Nino index as our data. And if you're not familiar with what El Nino and La Nina are and why they matter for climate and weather, here is an excellent, quick 2-minute video from NOAA about that. If you're already familiar with El Nino, feel free to fast forward through this.
Warmer or colder than average ocean temperatures in one part of the world can influence weather around the globe. Boggles the mind, right? Here's how it works. During normal conditions, trade winds, which blow from east to west, push warm surface waters towards Asia, piling it up in the western Pacific. In some years, though, the trade winds weaken. The warm surface water moves eastward and reduces upwelling of cold water off the coast of South America. Climatologists call this El Nino. Its climate impacts show up mostly in the wintertime over North America. The warmer ocean fuels an intensification and southward shift of the jet stream. This brings flooding to the southern United States and warmer, drier conditions over parts of the Pacific Northwest, northern US, and Canada. But eventually, those trade winds pick up again and sometimes become even stronger than normal. When that happens, they blow the warm water back into the western Pacific and restart the upwelling of cool water towards the surface in the eastern Pacific. These strong trade winds are a signature of what is called La Nina, unusually cold conditions in the tropical Pacific that displace the jet stream northward. La Nina can lead to drought in the southern US and cooler temperatures, heavy rains, and flooding in the Pacific Northwest. El Nino and La Nina together are part of a cycle that influences extreme weather and can impact food production, water supply, and even human health, not just in the US, but in many parts of the globe.
Okay, hopefully you enjoyed that. So El Nino is really important. And that means that scientists have created indices to represent how its strength changes over time. And that's the easiest way to look at the strength of El Nino over the years. And that gives us a single number for each month. So if you search for El Nino index on Google, one of the top results that comes up here is from Climate Data Guide. And I'm going to navigate to that. And I highly recommend this website. It has brief primers on some of the most commonly used climate and ocean data sources. So it could be useful for your final projects. So this page explains the different indices that have been created to represent El Nino. And the specific one we're going to use is called Nino 3.4. This paragraph explains how this is calculated. So basically, Nino 3.4 represents the average of the sea surface temperatures in the central part, this speckled area of this box here, in the equatorial Pacific Ocean. So that means higher numbers of this index represent warmer average temperatures, and warmer temperatures are the signature of El Nino. So we're going to go to the Get Data tab of this website, and we're going to download this second Ni&ntilde 3.4 index from 1870 to present. So I'm right-clicking and clicking download link file. Those of you on Windows, you'll do that differently or in a different browser. And next, we're going to open that file using a text editor. So I'm opening it here, and you can see all the values for this index. And you can also do this looking at what's in the file by writing some code using the readline or readlines functions that we taught you. But I find it sometimes easiest to just open the file in a text editor. So for Macs, that's text edit. And we see that the data values here are separated by spaces, not commas. And it also seems that the rows represent years from 1870 to present, to 2020 down here. The columns aren't labeled, but there are 12 of them. So they're almost certainly the 12 months of the year, January to December over here. And we also see that there's just one line of header stating that the data goes from 1870 to 2020. And we're going to need to ignore that header when we load the data. If we scroll down, you can see that there are 5 lines of footer here, and we're going to need to get rid of those as well. Okay, so let's load this file into Colab. And here, remember that if you don't want to have to upload the file to Colab every time you open the notebook, the easiest way to do this is to just upload it to Google Drive. So I've actually saved it into this data folder that I've created in my Google Drive here. So here's that data, Ni&ntilde 34.long.data.txt. And you can see the file path at the top if it's more complicated. So I'm going to take note of this folder name and the file name, and then I'm going to type the file path into Colab. So let's say upload file to Google Drive, save file path, and we're going to give it the variable name file path equals drive/my drive, Ocean 215, data, Ni&ntilde 34.long.data.txt. Okay, so now we need to give Colab access to Google Drive. And we're first going to import the required module, access to Google Drive, from google.colab import drive. And then we're going to mount the drive. So we say drive.mount content drive. Okay, and I actually missing a slash at the start here. Okay, content/drive. And I run this, and this gives us a URL to navigate to. So when we get that URL, we're going to click it, and it opens up this page. I have to authorize it using the right Google account, allow, and we can copy that easily using this button over here. So we're going to go back to Colab, paste it in here, hit return, and it works for a little while, and it says that we're mounted. Okay. And next, we're going to use that file path to load in the file. And for that, we're going to use NumPy's gen_from_text function, since we've already looked at the file to see how many lines of header and footer there are. So for that, we have to first load import NumPy. I'm just going to say load file using into Colab. Import NumPy as np, as always. And then we're going to use np.gen_from_text. Okay. And we give gen_from_text the file path as our first argument, then the number of header files. So we're going to say file path, the number of header lines. Then we say skip header is 1, because earlier we saw that was 1 line. And then we need an argument to get rid of those 5 lines of footer text at the bottom. So if we hover over this function here, we pull up the documentation. Hopefully, sometimes it takes a little while. And sometimes it doesn't appear at all. And you know what? We can actually get that using a different strategy. So we're going to say np.gen_from_text ? And that will give us that documentation. Okay, here we go. And we see that that argument that we need is called skip footer. If you want more details about that, you can scroll down. And it's not really nicely formatted, but you can see all the details about the different arguments over here. Okay, so we're going to close that documentation. So we need skip footer. is equal to 5 because there are 5 lines. And we need to specify which columns to load. Okay, and now the documentation is popping up. And we just want to load the first column this time, the years. So we say use calls equals 0 for the first column. And we need to tell it the data type of the years, which are integers. So we say dtype equals int. And then lastly, all those values were separated by spaces, not commas. So we need to write delimiter equals none. Or we can also just leave out that argument if it's none here. Okay. So let's run this. And there we go. Awesome. It loaded all the years. But since we didn't save that result to a new variable, it just printed everything. So let's actually save that to a variable called years here. And now when we run this, looks like nothing happened, but it saved. So those years were loaded as a NumPy array. And let's just check the shape of the NumPy array that we called years. So if we do print years, years.shape, say check dimensions of the years NumPy array. When we run that, it says it's one dimensional, so length 1 tuple, and has a length of 151. So there are 151 years. Okay, now let's load the rest of the data columns for each month of data. And here we're just going to copy and paste this line from before. We're going to call it data. This variable is called data. And we're going to specify this time that we want to load the columns 1 through 12. So we're just going to write range 1 through 13 because it's exclusive at the end. Okay, so it's going to load columns 1 through 12. And now those data types had decimals, as we saw earlier. So we're going to say data type equals float. Okay. Looks like it loaded without any errors. Let's check the dimensions of this array now. So print data.shape. Okay. Check dimensions of the data NumPy array. And sweet. Okay, it has 151 rows, 12 columns, 1 for each month, as we expected. And we can just print this array to make sure everything looks right. So let's go print data. Say get a preview data by printing it. And that looks pretty good. You'll see that Colab has put in these ... ellipses over here, and that's telling us it didn't print all the data. It truncated it just to save space. But it looks good. Except you'll see on this final row, which is data from 2020, there are a few years a few months that say negative 99.99. And that's a very common placeholder for missing data. In this case, if you open up the file again, you'll see that these missing months are September to December of 2020, which makes sense. It's recent data. And that's not good. Those values are going to mess up things if we take the average of all this data or if we plot it. So we want to change those values to np.nan, which is our placeholder value for missing data. And we're going to do that using conditional indexing, which I introduced in lesson number 5. So we write data for the values of the array data, okay, where, and here we use brackets for indexing, where data is equal to negative 99.99, change those values. So we're using an equal sign to modify those values, change them to np.nan, which is our placeholder here. I'm just going to write a comment here saying that we are masking out missing data using np.nan placeholder. Okay, so we run this, and now if we print the array again, hopefully those values will be changed. So we do print array, and there we go. They're not ands. Okay, so next we want to plot this data. But in order to do that, we need the array in a one-dimensional format because it's really just a time series that's been provided to us in a two-dimensional array format. And we can use the NumPy reshape function to do that. So we say the variable data1d, we're going to call it that, will be the reshaped version, np.reshape, of data. And we want the new shape, and you can see the documentation is pulling this up here. New shape is going to be 1D, so it's a length 1 tuple, in parentheses, with a length of 151 years times 12 months, comma, because it's a tuple that is length 1. Okay. So this should work, but remember, we don't want to hard code values. So a better way we can get this is using data.size, which, if you remember, is the total number of values in data. Okay. So we run this. Let's just print this over here, see if it ran successfully. Print data 1D. And indeed, it was shaped successfully into a 1D array, which is what we want. And note that there's an even easier way to flatten 2D arrays into 1D arrays, and that's using NumPy's flatten function. So we could have written this. Data 1D is equal to data.flatten. And notice the syntax is a little different. You're calling it on the object data. And that should work too. Okay. So back to our goal of plotting this data. Well, line plots require you to plot x values against y values. And the data over here, this 1D array, are the y values. So we're good there, but we don't have an array of x values yet. And for that, we want the times from January 1870 to December 2020. So we need to create that time array. And that's going to look something like this. I'm going to copy and paste this from what I have already typed out. So copy and paste that in here. So it's going to look like this, except instead of what I wrote here, it's going to be date times. So from January 15th, 1870, February 15th, 1870, all the way to December 15th, 2020. And note we're using the 15th of each month because monthly average data should approximately represent the midpoint of a month rather than the first day or the last day. Okay. And one way to assemble this is from 2 long arrays. One with all the months that repeats from January to December 1870, then January to December 1871, then January to December 1872, etc. And then a second array that's a list of years. Okay, so that would have 12 1870s, then 12 1871s, then 12 1872s, etc., all the way up to 2020. So let's make that first array of months. And here we're going to use NumPy's tile function, which repeats a list or array a given number of times. So if you write all months equals np.tile, tile, and here we're going to give it the range function from 1 to 13, so months 1 through 12, comma 5. Let's just say repeat them 5 times. Okay, so what does this do if we print all months? That looks right? It's doing this 12 times, repeating the months from 1 through 12. But we want it to repeat once for every year. So instead of 5, we want it to have length of years for that argument, which is going to be 151, right? So we run this again, and it's not going to print the whole thing as truncating because it's so long. But it worked. Okay. And now we want to use a similar strategy for the years, except here we're going to use NumPy's repeat function to repeat all the years 12 times for each month. So we're going to say all years equals numpy.repeat, range, this time 1870 to 2020. But wait, it's exclusive, so we need to say 2021. So 2020 is included in there, comma 12, 1 for each month. And let's print all years. Okay, and that looks right. It looks like 1870 was printed a bunch of times, and it ends with 2020. That's what we want. And that means that we are ready to assemble our datetime array. But first, we have to import datetime. From datetime, import datetime. Okay. And now the easiest way to merge these 2 arrays, these long year and month arrays, is using a for loop, or even better, a list comprehension, which again is just a way of writing a simple for loop more compactly. So I'll call it datetimes, plural. And I'm going to set that equal to a list comprehension. So this empty list here, looping over an index. So for each index in a range function that gives us 0 up to the total number of data values, which is data.size, create, and again, I'm going backwards here, writing the for loop part first, create datetime objects filled with this information. where each year is selected from all years, the array we created using the index IDX, where each month is selected from all months, again using the index, and where each day is always the 15th day of each month. Okay, so we have a list comprehension saying date time, this information for each index in this range function. And let's print this, date times. And great, it looks like it worked. We start with 1870, January 15th. We go up to February, March, etc. And it's a lot to scroll through, but I think we can feel confident that this worked here. Okay, and because we always prefer working with arrays, not lists, let's just convert this into an array. So let's say date times equals np.array date times, because we prefer arrays. Date times. Here's a little easier to see this. Okay. So finally, we're ready to plot the data. So first, we have to import matplotlib.pyplot as PLT. Okay, import matplotlib.pyplot as PLT. And first, we're going to want to set up our blank canvas, right? And we do that using the subplots or the figure function. Katie showed the subplots function, and that's useful if you're making multiple plots. But since we're just making one plot, we can set up our blank canvas using just plt.figure. Simple as that. And if you run this code, you'll see it says it created a figure. I don't know why it prints twice. It's a quirk of Colab. And next, we can make a line plot of the data. And that's this essential plot function, plt.plot, which takes the x values, the date times, and then the y values, which are that array, data 1D that we created. Okay. And you can also call this on an axis object, sort of like you saw in Katie's video. But if you just use plt.plot, it will print to the current set of axes, which for one subplot in a figure is going to be the right one. Okay. So let's run this, and sweet, look at that. I plotted. Starts in 1870, goes to 2020, looks good. And these y values are around 27 degrees Celsius, because if you remember, they represent sea surface temperatures. And clearly this index wiggles up and down a lot over time. We might want to see that more clearly. So let's specify a longer figure using the fig size argument. Okay, let's say 16 inches long, 4 inches tall. See what happens here. And that looks a little better. Okay, we can see things more clearly now. Well, what if you wanted to rotate this? So date times were on the y-axis, and then these temperature index values here were on the x-axis. Well, just for the sake of demonstration, you could do that. You would just have to switch these arguments, right? Data 1D, comma, date times. You might also want to switch the orientation of the figure too. So here we go. It's a long and tall figure. Let's change that back. Let's keep it horizontal. So let's do 16, comma 4. And let's say date times, comma, data 1D. Okay. And now I think we might want to make this plot a little prettier in appearance. So let's change this line color to black instead of blue. And we do that by setting the color argument. So a common shortcut for color is just C. But you can also say color equals, let's say black. Run this. It works. Okay. And yeah, the shortcut is C. You'll often see that. And the shortcut for black is actually K. C equals K. Okay. And that gives the same thing. And you can find all these color options in the matplotlib documentation at this link that I'm just going to copy into here. Okay. Copy paste. And I've loaded that up here. You can also just Google matplotlib colors. That's usually how I get to this page. And if you scroll down, you can see all these shortcuts. So you can see those, or all these named colors. You can see the shortcuts up here. You can see the named colors down here. You can create some beautiful art using matplotlib. So we're going to go back to our Colab notebook. And one thing is this line is fluctuating so quickly that it might be easier to see these changes if it was a bit thinner. So we're going to change this line width. So we can use the documentation website or this built-in Colab documentation here to find what that argument is. So we hover over here, we can scroll down inside here to the various parameters. And if you scroll down, you'll see that line width over here has a shortcut LW, and it takes a float value. You see all these different ways to customize the plot. So we're going to say LW is equal to, let's try 10. See what happens. Okay, whoa, way too wide. Let's try 1 instead. How does that look? That's a little better. Okay, let's work with this. And you could endlessly customize this, but let's just, just show another thing here. This is going to be useful for assignment 2. Let's try adding the actual data points onto the plot. We do that, of course, using the plt.scatter function. And it takes the same thing, x values, date times, y values. Plot that. Okay, so it added all these dots, and they're way too big, and I don't really like blue. So let's make them smaller and change their color. Okay, and again, we can use the documentation. Hover over here, pulls this up, and skip to the bottom. But okay, and we see over here parameters. We have this S parameter for size, S argument, and then C for colors. Okay, so let's give a size of 4. And then colors, let's say dark orange. Colors, because Halloween. Okay, let's run this. There we go. That looks a bit nicer. So as Katie said, every plot needs to be properly labeled with the title and axis labels, including units. So let's do that. And here I'm going to use a simpler syntax than what Katie showed in her lecture. Again, that syntax that she showed is more useful if you have multiple subplots in the same figure. Let's give it a title, plt.title. Say Nino 3.4 index. Okay, and we give it a string. Same thing for the x label, x-axis label here, say time. And then y-axis label. Here, let's say average sea surface temperature in degrees Celsius. We can put units in the parentheses over here. Okay, so we run this. What does this give us? Nice, we have a title, we have the x-axis label, and we have the y-axis label. And sometimes it just prints out this text thing. If you want to get rid of that, you can just add a semicolon to the end of the last line, and it will plot without that. But it's not a huge bother. Lastly, let's add some grid lines using the grid function, plt.grid. Okay, we run this, and nice, we have those grid lines. So that's actually all for this lesson. We're going to use what I showed here as a foundation for Thursday's class, where we're going to get into some more demos that will be useful for assignment 2. So save this, annotate this, keep it as a reference, and I'll see you tomorrow in class.